Sir, good morning, sir.
Good morning, Professor. How are you?
I'm good, sir. How about you, sir?
I'm doing good. Give me a second
Yes.
to connect my headset. Okay, can you hear me okay? Professor Suresh.
Yes, sir. You are audible.
Is there any noise?
No, sir. No, sir. Nothing like that.
Ah, excellent.
So actually, yesterday we had some overlaps regarding the labs, sir. Actually, so that's why there was a delay in joining yesterday's session.
No problem.
So apologies for that, actually.
No, I
Because
remember you mentioned. You
yeah,
mentioned that there were
because the thing is, unknowingly, some other department faculty they have like reserved that particular lab for their events, sir. So we are not aware of that, and even they were not aware of our sessions.
no problem. And I know students are able to pick up something out of these sessions. And I hope these sessions are not just becoming recontract.
Sir.
I hope the students are able to pick up some concepts and some code knowledge. What do you feel? Anyone?
Sir, if you don't mind, there is a slight disturbance in your voice, sir.
Okay. Is it okay now?
Yes, sir. Much better.
Yeah, I was saying, I hope that the students are able to pick up the concepts from my sessions and as well as able to get started in building the models or building the finance.
Yes, sir. Yes,
Reach
I
out
guess.
to you.
Yes, sir. They started, and I hope they are working on it, sir.
Someone reach out to you.
Sorry, sir.
Did some students spoke to you or reached out to you or reach out to
Yes,
you?
sir. Like I was asking few students like whether they have started the things and they are whether they are able to understand the things or not.
Okay.
Yeah. So like they were conveying like yeah the sessions are useful and yes of course they are able to follow. And the thing is like they very recently they have started these topics according to their syllabus.
Right.
So I hope they are able to follow now compared to the previous 2-3 sessions. Yes, sir. Yeah. So let us wait for 2 minutes, sir. Students may join so that you can start the session.
I think we still are at 10:20. Yeah, now 10. Yeah, these are a bit of, what should I say, little dry concepts like mathematics, models, how can I do it? But in reality, these models actually originate from many things that we would have done as a child. I don't know if you can have that. I do distinctly. We used to do some game called guessing the name of the movie the other person thinks. Just put down a list of 20 or 30 on a paper
Sir,
and
excuse
then
me. Sir, excuse me, sir. Sorry to interrupt you. There is slight disturbance. I mean, your voice is breaking, sir.
check. Oh, it should be far better now.
Yes,
Right.
sir.
It was picking up the laptop microphone rather than my headset microphone.
Okay, okay. Maybe that must be the issue, sir.
And then my yeah, far clearer now and crystal clear actually.
Yes, sir. Yes, sir. Students, can someone confirm, sir, whether his voice is clear or not?
It's
Anyone?
clear, sir. It's clear.
It's clear?
Yes, sir. Yes, sir.
Excellent. Yeah. So I was saying, all these mathematical models are formalization of what we used to play as children in our childhood, some games, right? One that I particularly remember, maybe some of you have had a chance to play, is that we used to carry a paper, at least I have done that, where we had 20 or 30 movies written down on the first paper. There used to be slots that were slotted out on the right side with some numbers, and we used to ask them simple arithmetic. Take the number of the movie that you've guessed, add something, multiply something, divide something, deduct something, and finally you will arrive at a number. And then you know that number because you've used some math, and then you ask him to open that, and then you can find that movie name. So the point is this: these are all something. These models, those sound abstract, mathematical models used for the machine learning. They all emanate or originate from what we are already familiar with in a crude way in some part of our life. So it is the interest of the student or the learner that digging deep would help you become an expert in those models. These are all simple mathematics. So anyone else will give another 2 minutes. We'll start at 35. Is that fine, Professor, or should we wait for 10:45?
No, sir. Like let's wait for another 2 minutes.
Right.
Then we may start, sir.
So
Yeah, I think what you said just now was exactly like true, sir. Like we used to play the things, and which later they became the models.
right. All of us know many of these things because they're not coming out of any other world that we are not familiar with. It's the focus and interest. And yesterday we talked about sensitivity and the specificity, right?
Yes,
Being
sir.
sensitive to the information and being specific to filter out the noise, sensitive to the facts and specific to filter out the noise. That's what matters. Not only in machine learning or becoming a machine learning expert, but also to become a better individual, not only in the business or in the academy, but also in the society and in the family as well. So we have another minute. If any of the student would like to share any feedback, I have requested feedback survey. I think only 16 or 17 have been filled in. If anyone wanna share any feedback, guys, or share anything, it would immensely help me to make these sessions more interesting and more useful for you. If you guys speak up and share your feedback, there's nothing wrong in sharing feedback. I remember I'm not an expert or I'm not perfect in any topic, but I'm a perennial learner. So if there is something that I can improve that would benefit you guys, I would be happy to. So please speak up. If you have something that you wanna have me bring that change in here, right, guys?
Students, you can unmute yourself and you can convey the feedback to sir. So how you are learning the things and how you are able to understand and how they are helpful for you guys. Anyone, like whoever is interested, like, and whoever is willing to speak.
So this is the feedback I have received. 16 students or so. This is the second feedback. I see many of the students. I have never seen any below average rating or feedback, but many of the students are enjoying, as it is clear, extremely useful. The content of these sessions are around more than 50%. But I'd like to make or bring the other 50% students as well to the level of enjoying it extremely useful or feeling it extremely useful, which happens when I bring my content to in the tuning level, or tune the content to the level that they would enjoy, they would understand. That is what my effort and my request for you guys also to help me and express how I can bring in from your perspective the content and the sessions that can make you feel this is extremely useful. The content is extremely useful, right, guys? So there is one person said that pace is okay, but it can be increased. I think I'm slowly increasing the pace. Somebody requested for changes in timings on Sunday. That I'd leave it to Professor Suresh to talk to students and or coordinate with the students and let me know a time slot, and then I can see if I can.
I'll do that, sir.
Yeah. So if I can, change the time slots, sessions to that slot.
Yes, sir. I'll speak and I'll take the majority people's opinion as the final one.
Right. Definitely. And somebody said the pace is slow. Um, so I'll definitely try to increase the pace. And good, but some prerequisite for the session will boost our interest. So this feedback was given as well in the first session, and I have been cautiously trying to bring in lots of prerequisites. Any key term that I mentioned in the session, I make it a point to spend some time to help detail what that key term is. But definitely it would be my endeavor to perpetually and perennially to define or to address those prerequisites, or essentially all the terms that are used, all the concepts that are used in the projects, right? So anything else other than this feedback, guys? I hope to for at least some 80 to 100 people giving the feedback, because we are around 150 or 147. But it is unfortunate to see that only 17 have filled in. It definitely reflects definitely one of the facts, one of the points that it reflects one of the points that I'm not making these sessions enjoyable or interesting to others. Obviously, majority of the people seem to be not interested in the sessions, but it's okay. I've been a student as well. So try to extract something useful for these from these sessions, because one day you will feel, oh God, I should have attended those sessions because my job is demanding it now. And I am quite certain that such situation would come pretty shortly. In fifth semester, another 3-4 years, you would definitely get to that timeline. Having said that, if anyone want to give any feedback, we'll spend a minute, else we will jump into the today's session. Ladies and gentlemen, anyone want to speak up and share your feedback to make these sessions more useful for you? All right, looks like no one is interested, so we'll get going. So good morning, students, ladies and gentlemen. Yesterday, obviously, I spent more time in explaining the logistic regression model, mathematics behind it, and obviously key concepts. I also walked you through what's the project about, and I've also walked you through the project and demonstrated the output. This time my project is, I actually wanted to build two versions of the project. One, without using any, if you recollect, I said SMOT, etc. techniques, grid search and solver selection, regularization, all that, right? Without all that, a simple model using a simple binary classification, maybe using a standard scalar, and then convert one hot coding, which is essentially to transform the categorical values into something that the model understands, right? Using one hot encoding, there were around 3 to 4. And the other version was, let me take a step back. So the first simple version, and then look at the accuracy. Definitely it would be much, much lesser, probably around 50%. We'll talk about it why. In fact, I'm going to ask you guys, take this as an exercise to carry back home. And build the other one using enhanced techniques and use or deploying or employing these tools that would address some of these challenges in the data, right? Which is a real world problem, right? And we'll talk about what are those challenges, why accuracy is lower in this model. But use that, build that enhanced model using those techniques, SMOT, etc. Somehow I didn't get much time, so I straight away coded the SMOT using all these enhanced techniques. So we'll spend some time in terms of these two sessions, right? So did anyone have a chance to complete the coding and see the accuracy or share the accuracy what they have achieved? Anyone? None?
No, sir, we didn't do anything, sir.
Okay, all right. Then let's get going quickly so that we can do something now. All right. So today's focus would be more on the code, more on the accuracy, or rather on the code, accuracy, and the techniques to improve the accuracy, and understanding the concepts behind those challenges and the techniques to improve the accuracy, right? So I'm essentially using yesterday's slides, but I have added some more. Obviously, I'll be publishing these slides as well. And I hope you had a chance to see whether you are able to access the yesterday's recording as well as the slides. They have been published. The link has been published, and they're published in Google Classroom. Right. All right. So, we started with, why can't we use linear regression? Because in the case that we have chosen where the outputs or the response variables are discrete, non-continuous variables or values. So they are discrete, they are categorical, they are ordinal, order 0, first, second, third, fourth, right? Hence, it looks a little challenging how a model, which is linear regression, that helps us predict continuous values. How can we convert continuous values between categorical values, whether two categorical possible outputs, binary regression, or more than two, which is multinomial regression? And then we've established that we need some sort of function, a logistic function that would transform the linearly regressed values, right? Linearly transformed values using the regressors and the regression coefficients, nothing but weights and the features, transforms into something between 0 and 1 as this plot shows, which we call it as sigmoid function. And we've looked at the definition of the sigmoid function, and then how the model uses the sigmoid function to arrive at binary predictions 0 or 1, based on a simple rounding. Greater than 0.5 if the value of the sigma function, then it's 1, less it's 0, right? And sigmoid function is obviously a most favored curve mathematically, because it's smooth, it has the gradient, a smooth gradient, and it is continuous, it's not broken. The curve is continuous, there's no breakage anywhere here, nowhere it's broken, right? If it is broken, then we don't know what's the its slope or its differentiability at that. Anything that is broken.
Excuse me, sir. Sorry to interrupt.
Yeah.
Sir, are you been sharing the slides, sir? Because I can see only the welcome slide, and apart from that, on my screen I can't see.
I'm sharing the slides. Maybe there is an issue. Students, can one of you confirm whether you can see slide called logistic regression model and the logistic function?
Yes, sir.
Do you
So
see?
it must be issue from my side. Let me check. Retry it once, sir.
I can reshare, just a second.
Yes, sir.
Professor Suresh, I have reshared. Is there any change in your frame?
Let me check. So I think it's loading. No, sir. Like I can't see that particular slides. Maybe it's an issue from my end. Let me sort it out.
Okay. Students,
Yeah.
can you see the slide titled Logistic Regression Model and the Logistic Function?
Yes, sir. Sir, we can see, sir.
Okay, excellent. Thank you, Chakradhar. Thank you, Vishnu. Thank you, guys. All right, so it's smooth, it's continuous, and if it is broken somewhere here, let's say, right, that means we don't know the values. That means we can't establish its slope, its rate of change, which is nothing but your first derivative, and also is nothing but your slope, right? So this sigmoid function is obviously most favored curve, but it has its own pros and cons. You'll see that when you get to neural networks. But nonetheless, this particular sigmoid function representation, mathematical representation, which I just drew a rectangle around, is nothing but your neuron. A neuron is nothing but it's a simple processing, right? A biological neuron essentially visually sees something and then arrives at some inference. If it is an equation, it will try to arrive at some value. If it is a visual picture, it will try to arrive at what picture is it? Again, at discrete values, right? So these basic traits of or nuances and analysis of these nuances or situations are super critical for us, for you, for us as engineers, particularly AI and ML engineers, to understand, to take a deep dive into, because the solution lies in understanding the basics, right? Anyway, so we've then looked at the limits of the sigmoid function when the linearly regressed or linearly transformed value lies between minus infinity to plus infinity, and the half point when it is 0. And obviously we've looked at the plot or the graph that captured these values between minus infinity and plus infinity for the z value, which is nothing but our linearly regressed or linearly transformed values. Linearly transformed values of the feature values multiplied by respective weights or coefficients of each feature, which is nothing but our linear regression, right? So we looked at the example and we looked at predicting or identifying or defining the probabilities of the predictions, particularly in the context of binary classification or the binary logistic regression. And then we derived what is the probability for the class 1, which is yes, true, success, or what is the probability of class 0, which is false, no, failure or fail, etc. 1 minus gx and the gx. And then we've also looked at, in fact, I hope you had, some of you had gone through how I have derived the update rule for the coefficient, not matrix, coefficient vector, which is W, the weight vector, iteratively arriving at its value based on the training data, based on the joint or joint likelihood. It's essentially driven by maximum likelihood, and maximum likelihood is nothing but a joint probability of certain set of inputs, a vector, input vector, with an outcome. Outcome is 1. So outcome is either 1 or 0. If it is 1, 1 comes with what are all the possible input combinations. So we also talked about, n choose or combination part of it, and taking it's essentially log likelihood. You take likelihood and then a log of that, and then you would arrive at the update rule, which is nothing but this. And this update rule essentially is a key piece. This is also called online learning. Across the machine learning models, particularly if you are improving your model on the fly based on the user actions on a website or in an app like Amazon, Flipkart, this update rule to update your coefficient vectors, your feature vectors, is used. So better watch out, better dig deep into it and understand this. And it's pretty simple. If you look at it, is simple basic arithmetic, right? So what was your previous prediction? And then you should be able to make some correction to your previous prediction based on the, to arrive at the current prediction. Or prediction here is nothing but your vector. So you know the previous vector, which is nothing but your regressor coefficient vector or weights vector. And then there is some step value or the learning rate, some arbitrary or random value, which you would modify based on certain parameters. I'm not going to go deep into it, but make it simple. Then what is the current output value? And what did you predict based on the previously predicted coefficient vector? And then what is the current input value? So this difference is nothing but your prediction error for the current sample, right? So we looked at the online learning, online update or online learning model. So please remember this, you would need it forever if you're building AI ML career, right? And then obviously we looked at the model evaluation metrics, the first being the accuracy, which is straightforward. How many did I get wrong out of n, right? And confusion metrics, very critical to understand these terminologies, these key terms of true positives, false negatives, false true negatives, and then false negatives, right? So confusion matrix is nothing but, what was the actual vector and what is the predicted vector in terms of any given value or set of given values.
where you use the total count for all of these 4 elements, right? And then we also looked at the receiver operating characteristic curve, the genesis of this, how it originated from signal processing and then the statistics. Essentially, people say it, right? And filter out the noise, right? And focus on the signal. And how the model is filtering out the noise and how the model is focusing on the signal, which is nothing but a pattern, which is in this case is predicting the right value, whether it's 1 or 0. And when these observations are plotted on a curve, that becomes your ROC curve, which is also used for this model because this model is as well predicting a signal out of noise. Signal is nothing but whether it's 1 or 0 or a categorical value. And then we looked at the positive rate, true positive rate, and then the false positive rate. Of course, this is just a summary of what we talked about. And then we looked at the true positive rate and the definitions and the mathematical formulae for those: true positive rate, false positive rate, specificity, and the sensitivity. Right? These are very, very important. Specificity, sensitivity. Sensitivity focuses on how sensitive you are in identifying the right answers. These are the terms not only used in machine learning, but they are used across any industry, any branch of science, right? When you are assessing the performance of some output, even in the quality engineering, out of 1 million products that Kia Motors builds in Seltos, badass car Seltos, how many of them are actually having troubles? That obviously goes back to the specificity part, right? But these are used in manufacturing, in any process engineering, and most importantly in determining, we went through the COVID test. Specificity, sensitivity were used, whether this test is what is its sensitivity, how much percentage it's actually predicting whether the test is positive, meaning the user or the patient has the COVID, or how accurately it's predicting when the test results turns out to be negative, how accurately it is negative. So these are very important. Essentially, the curve of the receiver operating characteristics curve the area of that curve should be 1. That is what we want because it's a ratio. Specificity and sensitivity should be always 1, because whether it's positive that you predicted or the negative you predicted, it should be 100% right? And then we looked at the F1, which is nothing but it's a harmonic mean. Yeah, I haven't talked about it yesterday, so let me spend some time. So harmonic mean is nothing but it's an average. It's a statistical term. So you must have studied in statistics if you've taken undergrad statistics module or credit, right? The formula is very simple. This also goes back to probably in a way related to Fourier series. It's a harmonic, Fourier is nothing but any value, any signal can be decomposed into multiple harmonics of different frequencies, essentially sinusoidal waves, cosine and sines, right? So an average, it's an average. And how is it calculated? It is calculated by dividing the total number of values in your training, which is n, right? Maybe in this case, I think 3 lakhs. Sum of reciprocals of each value. And this gives essentially, it's a average of ratios, right? So since we talked about FPR and TPR, these are ratios, false positive and true positive. We would like to look at the harmonic mean, right? So the formula F1 is 2 times the precision times recall divided by precision plus recall. So precision essentially says how out of the predicted positives, how many are really positives, actually positives, which is your sensitivity. Recall is out of actual positives, how many did we correctly predict the positives, right? So significance of F1 is, if it is very low, if the F1 score is low, harmonics, precision or recall are low, the F1 would also be low. This reflects model isn't performing well overall, and it has to be higher value, potentially 1, because it's a ratio, right? Then, so key takeaways, logistic regression is straightforward, simple, particularly useful and powerful for binary classification or binary prediction problems. And of course, it is important to have proper data processing and also handling something known as class imbalance. We'll talk about it. In fact, that's where I want to spend more time. And these are important, you know, if there is an imbalanced data, handling that is also important to have a proper model that has better accuracy for predicting unforeseen data, right? Or predicting the outcomes for the unforeseen data. Of course, the real world problem, if you look at the data, is it balanced? The training data, the outcome data, or is it imbalanced? We'll get into it shortly, right? So we looked at the project overview of predicting the, if an existing customer, an incumbent customer, who is a customer of ICICI Lombard, who bought the health insurance, will that person be interested in buying vehicle insurance, if which will help ICICI Lombard to invest in building marketing and a business itself for selling the vehicle insurance. By the way, it's a hypothetical problem. It is not true. ICICI Lombard already sells all sorts of insurances, particularly health insurance as well as vehicle insurance and various forms of vehicle insurance and health insurances. But this is a little imaginary problem, right? But this is a true problem that many of the businesses which would like to venture into related business segments or lines of business would like to have some mathematically proven data to invest. In fact, you would face this much more as you come out of the college, university, and as you start thinking of starting your own company. When you have an idea, you need to build models to say how your revenue or your product is going to grow in terms of the revenue, in terms of the profit, in terms of investment needed, capital needed. And you need these models to present to your potential venture capital investors or seed investors or angel investors. So these are super important to understand these concepts, right? So this data, this project has obviously the data of existing customers who bought the health insurance, and this data comprises across 10 features, 10 columns, gender, age, vehicle damage. If the vehicle is damaged, what was they've collected some training data across. It's a huge data, around 3 lakhs, and this is easy to collect through app or through the website. We've talked about it yesterday, right? And then the metadata about the data, the training data set, 3,81,000 plus rows of training data, and prediction is expected for 1,27,000 rows of users. Features are 10, and some of them are categorical values, and most of them are continuous values, right? And some source, data source information, and what needs to be submitted, a separate CSV, right? And then implementation steps, which are again standard, right? So let's go through the code and the output, and then come back to this slide. So let's go back. Let me pull up the Visual Code, Visual Studio Code. All right. Let's see. All right, guys. So we haven't got shell code. No? Oh, really? Let me check. Let's check. Classroom. So when you say we haven't got shell code in the Google Classroom, I thought I had uploaded. Let's check. 3, 4, logistic regression, announcement, new material, training, insurance. Oh, I see. My apologies. Let me upload it right away. So it should be in my drive. It should be in guest lectures, GPREC, GenAI Lab, August. So it should be where under lectures, week 4. Project should be under project, under announcement. Where is the file? This is the shell code. Yeah. All right. Now you guys should be able to see the shell code. Can one of you check through your mobile app? Vishnu, can you check on the classroom app? And
Sir, seconds, sir. 1 minute, sir.
Sir, I guess it may take a few minutes to reach the destination.
okay, but
Sir, we
usually
have received, sir.
it should be instantaneous. Okay.
Yes, sir, they have received the shell code, sir.
Okay, excellent. All right, so now let's go through the code. So these are imports. Hold on. Okay. So these are the needed library imports. Luckily, lots of good kids have built the code and offered it through the open source as part of the, the package libraries or package management of Python as part of pandas or scikit or matplotlib. Thanks to them. And then this is a little housekeeping of creating a watermark image blob so that we can paint it, render it as a background watermark in the plots. Give me a second. Right. Then we have, so there is a method. We have gone through this method earlier. So essentially, this method adds watermark to the plot, given the plot context, watermark blob, and then alpha. Alpha is nothing but your transparency, how transparent the image or the watermark image needs to be, and how much zoom that we want the image to be. So it's a less than 1, which means we are zooming out, essentially zooming in, so reducing, shrinking the image so that it fits into the area of the plot in the background, right? So that's this code. We are loading the train and test data because this time we've been given with the train and test data in 2 separate CSV files, comma separated values, right? And then we are checking for any missed values essentially in the training data set. Is there any row that has a missed value for any of the feature / column, right? And then we are doing the pre-processing by means of the next step of pre-processing. This also is pre-processing, essentially the step of finding the missing values. Had there been any missing value, probably we would have added some value, right? Inserted some value. If it is a continuous variable or the feature, what value we would have inserted in the missing place? Anyone? Any guess? Average value of that column, right? And if it is a categorical feature or a column, then we would have added some missing a new column and some value, ordinal value corresponding to that, right? Or category value. So we are encoding using this philosophy. We are encoding all these categorical features, right? And then what are we doing here? So we are separating the input feature vector from the table, from the CSV, and the response as two separate vectors, right? Essentially, X is a matrix, whereas Y is a vector. What is the size of Y? Vector size, guys? Any guess? How many training samples we have? How many training samples we have? 3,81,109, which means there would be 3,81,109 responses as well, which means the size of Y here would be, the vector would be 381,109 elements in that vector, right? Then we are obviously splitting the 3,81,000 training samples into train and test, with the 20% being the test samples. This test as in to test the trained model, right? Not for the prediction. So we have a separate CSV called test that is given to you to predict the values and submit. But this is to train your model and predicting whether my model that I'm training is getting to improve it, essentially, right? And whether it is perfectly working or not, or whether it's what's its accuracy, whether it's perfectly predicting or not. And then, so here, now it is time to talk about this mode, right? So I'm going to go back. So like I said, the code that I put in takes into account some of the challenges that are present in this particular project, or building the model for this particular project, and how to address them. So there are 3 challenges in this model that I had built. Right? So let's try to understand these 3 challenges. But apparently it's only one challenge, but when we dig deep, you will have a clarity of the other 2 challenges. So the model that I built, or the code that I had put in, essentially gave me 68% of accuracy, as you can see here, right? So actually it's called validation, not test. That 20% is the validation set. Whereas in linear regression, I think we saw in excess of 90% the accuracy, at least above 80%, right? So 68% of accuracy means what? So roughly around, we are guessing 50-50. We don't need this model, right? We can also look at any sample or any input and say, oh yeah, he may be interested, he may not be interested. We can also say that as a human, right? Or randomly put some values. But when we do that as a human, essentially, we are driven. If I am doing it, I may put based on my own understanding, my own biases or preconceived notions. That's the term, English term for bias, right? I may predict a particular value as 1 or interested, the customer, where if it is given to you, you may predict as 0. So then there is a no consistency. So the models, essentially mathematical models or the machine learning models, will help you bring that consistency and also refine identifying the patterns in the data, right? So hence we definitely want to rely upon mathematical models rather than humans predicting it. And also there's a limit to the human to look at each row, each feature and predict. It's slower, whereas if it is done by a machine, the rate is phenomenal. Machine works at the speed of nanoseconds, if not microseconds, if not nanoseconds, at least microseconds. Right? So the accuracy is low. What could be the reason? Let's also look at the second metric, right? The confusion matrix. Right? Also, as you look at it here, right? So let's say this is the actual axis and this is the predicted axis, right? So let's say predicted axis. So in predicted axis, we have predicted, what is this? 1601, essentially. What are those? Actual ones we predicted as 0, 1601. They were supposed to be ones, but we predicted them as, the model predicted as 0. Obviously, it's sizable. But if you compare that with the number of the prediction set or the validation set, which is around 20% of 3 lakhs, is how much? 60,000, right? So we have around 3 lakhs, 3 lakhs 7. How much was that? Let's look at it. 3 lakhs 81,000, approximately 4 lakhs. 20% of that is around 80,000. So around 70,000, 65 to 70,000 data points. We are predicting 1601 as wrongly zeros, even though they are supposed to be ones, which means the customers might be interested, right? Or not might be, they are interested. This is from the training data set. Now, out of our prediction of zeros who are not interested as predicted, they are actually also are not interested. So 44,276. So actually total is 45,000 change, not 80,000 change. Looks like the number was wrong, right? And also, if you look at the ones and zeros, there's a huge imbalance. Those that are interested are pretty much 90%, right? 44,000. Whereas those that are not interested, oh, I'm sorry, we have to look at this, right? We'll come to that then. Probably I mixed up. Let's look at the other predicted, other part of the prediction, right? So we predicted those that are interested in buying as actually they are interested. That number is only around 8,000. But we predicted those that are not interested, even though they are interested. Sorry, I think I got mixed up here. Let me clear it off here. All right, let's look at only this part. All right. So we predicted that 8,000 approximately are interested in buying, whereas actually they are interested in buying. So that's a correct prediction. Whereas we predicted 22,000 as not interested, around 22,000. They are also not interested, right? something wrong here, guys. Actually, they are interested. We also, yeah, that's correct. That's correct. So this here also it's correct. So our number is less, whereas what you can deduce from this picture is there is a huge difference or huge divergence or imbalance between interested, not interested. So when such the data is skewed heavily towards one outcome, you know, if you look at here, one outcome, the data, whether actual or predicted, the data is skewed or weighed or inclined towards less interested or zero interest or not interested people. That is how the data is. Right? If you look at the count as well here, 3,34,000 are not interested, only 46,000 are interested. Only 12% are interested, 87 or 88% are not interested. So data is heavily skewed or weighed or inclined towards not interested. So it is such skewed data will introduce what is known as bias towards the majority class. So majority class here is not interested. So our model also will try to predict most of the times are biased towards predicting zero result. So this is called class imbalance, the output class imbalance. Well, it may be a fact that many people are not interested, but unfortunately, that carries that pattern of inclination towards not interested or one particular class gets carried into the model, and that could disturb or that would bring the bias towards predicting more towards the class which has higher volume or density or distribution in the outcomes. So that is a problem, right? This would skew the results. The second is if the feature scaling, which we talked about it, and the standard, right? The values of, you know, your age, vintage is around few years, how long the user or customer has been a customer to ICICI Lombard, whereas the value of the car is in lakhs of the vehicle, if it is a car, or if it is a two-wheeler, few lakhs. Whereas the value or the vintage is few numbers, 1 year, 2 years, 3 years, 5 years, 10 years. So we need to scale them. So we've addressed sizably this topic in our linear regression. And the other one is something known as regularization, which we haven't talked about it. We've talked about standardization, normalization, but not the regularization. So we'll address what is regularization. So an improperly regularized data, which will essentially bring in non-regular generalization, meaning the model is not generalized for the unseen data. It has inherent bias and irregular. It's irregular as well. Right. So let's look at some of the components that would help, or some of the solutions that would help address or tackle these challenges that we have just found. You know, class imbalance, regularization, scaling or non-scaled data, or varying data, varying levels of scaled data in the training data set, right? So imbalance of the output classes in the data set, we've addressed, we've defined what it is, and then what does that mean? It brings in favorability. It's like nepotism, right? You know, if you are a relative of, let's say, a chief minister or MLA, it is quite natural to expect that you would get some favors in anything that the government announces if you're eligible, comparative to other persons that are eligible for that particular announcement, right? It's a favorability. In a way, it's a nepotism, right? And it's hard to get over with that nepotism. And of course, goal is to get rid of that favorability and nepotism, or take out that imbalance. And that's where the SMOTE helps. SMOTE is an acronym for synthetic minority oversampling technique. Let's just understand the English meaning of these, and then you would get what the heck is this, right? It is synthetic. What is synthetic meaning? Synthetic meaning it's artificially created. It's not naturally occurring. Anything that you synthesize is you create or you add, right? So we are creating something artificially. Let's look at what is that we are creating. Now let's look at the second word, minority. Something which is lesser than the other. So we are creating something that is a minority, right, in our data set. And of course, we are infusing this. Oversampling is essentially we are adding this in over and over, right? So we are sampling, we are oversampling, we are infusing the synthetically created data for an element which is minor, or for a class which is minor, and that is this technique. So which element or which class in our data set is in minority in terms of data distribution? We just saw it, right? Let me clear this off. What is a minority class here? This is the minority class. So we would like to introduce some synthetic rows with some values of the features such that we balance this imbalanced data, particularly for this class. So we boost it up, right? We boost up. Boost is the term also used, right? XBoost, etc. We learn them more advanced techniques. Right? So this technique helps. This technique helps to infuse synthetically class data with the entire data set, with the feature input as well as responses for that class which is in minority. In our case, it is essentially the target variable related to the target variable 1, which is where the user is interested. Right. So that is essentially the second bullet here says. So we are synthetically creating a minority class, resulting in a more balanced data set. You may ask a question, right? You are adulterating the data, which means you might be losing the pattern, the true pattern of the data. In a way, it is true, but it is not disturbing the actual pattern. But it is like you know, when you're taking a lemon in some juice, you may add a little bit of sugar. When you're adding some salt in lemon juice, you may add a little bit of sugar to bring the taste, right? It is something similar, right? It's also, I think, in your cryptography, you called it salt, so that you can randomize the data when you're hashing or when you're encrypting it. It's actually called salt, right? Some of you may know this. So it is something similar to the salt without disturbing the pattern of the latent pattern of the data that is present in the input training data, right? So that to that level, that much, it's not huge, not to the level of disturbing the original pattern, but to the level of rationalizing the mathematical model that we have built, which is essentially a combination of linear regression, linear transformation, and our sigmoid function. So these are all within the constraints. Mathematics is nothing but it's a convenience of creating certain concepts that can be repeatedly used and can produce the same result when you give the same input, right? So these are samples. So we will infuse this sample. So we are oversampling it vis-a-vis the natural data or the data that has been provided to us for the training. And this helps in model learning better about and from the minority classes, which will have a positive impact in rationalizing the recall, specificity, and the F1 score, right? So this would essentially help us reduce the false negatives. It will reduce the false negatives in our prediction. So that is smart for you. Synthetic minority oversampling technique. Any questions, students? Any questions? All right, no questions. So in the context of, let me address this. So there is also a regularization. We'll come back to this slide. Or maybe I'll address this. So there are two key terms which I've used passingly in my last 3 to 4 sessions. I'm sure I must have used at least once each of these two terms in all the sessions. Overfitting and underfitting. What are these? Right, and these would lead to something known as regularization techniques to regularize the model to behave rationally and normally for unforeseen data. These are the terms. Overfitting and underfitting are the characteristics of the model for the training data, right? So let's understand what is overfitting. So we are, let's first understand the meaning of English. So one thing that I would exhort to all of you to follow in your careers and in your academia is, without worrying much about what the concept behind any term that you hear for the first time, whether in your subject or in your exam or when you're doing your job or building software, is first try to understand the English meaning of it, which essentially means try to have a higher volume vocabulary in English, because this would reduce at least 20% of the challenges for you to solve a problem or to solve your question in the exam or to build the software that your manager has asked you to build. So what is overfitting? So it seems to be a combination word of over and fitting. And the simple English meaning is something is being fit, or we are fitting something, and that fitting is larger, over than needed, more than needed. Obviously, it's like when you try to stuff more items into a bag and you're traveling and you're trying to stuff more items into your bag, and if it is a cloth bag, it's going to tear up, right? And if these are the hard substance that you're fitting in. And something similar will also occur to a model. When you've already filled in your bag to the brink, more than a brink, and if you buy something during your travel and try to fit it in, it'll break. The bag will tear, right? And things would come out, or things would spill off or fall off, right? So overfitting is essentially model is extensively trained and extensively built to be 100% perfect for the training data, which means it's carrying the noise and also relevant details, right? So if you look at any data in the realm of human society, let's say some incident occurred in near Kondareddy Burj, let's say yesterday, and you ask your friend, hey, what happened there? And let's say 20 of your friends were present at that incident. Some fighting occurred, took place. One friend will give you one version. At least among the 20 friends, you may hear 2 to 3 versions of that incident, right? And each may have a different version, at least 10 to 20%. And there's also a corporate game called Chinese Whispers that you would play when you get into your corporate world and have some outings. So invariably, data that you collect in a sample, whatever it is in human society, it has variations, even though the fact that the incident that occurred, the fight that occurred was only one, but you may have various versions that people look at in different angles. And that may contain some noise. And that's essentially the fundamental assumption or fundamental rationale of any root cause analysis or any statistics or any mathematical model. So overfitting essentially is trying to build a model, mathematical model, that captures that noise as well. But a model, if you're predicting an unseen data, it should not be sensitive to noise, or the model should have been built being not sensitive to the noise, without capturing the noise or rationalizing the noise or minimizing the noise. That's where our optimization technique of bringing the error right between the prediction and the actual values, that is where we try to build the models, optimize the model to bring the noise levels or the error to 0. We may not achieve 0, but minimal, right? Whereas in overfitting case, we've built the model so perfect. You take any training sample, it will perfectly predict the exact value, right? Whether it's continuous or categorical, right? But the problem with this is it is perfect for 3 lakh data samples. But when you throw new sample, new customer data, it is not built to predict that because it may contain a different, because our model has taken into the noise as well, right? So it may not do well for the unforeseen data for the prediction. So that is the overfitting, right? So it is, the accuracy is high for the training data, but will be low for test or unseen data, new data. Because you built it so perfect to fit 100% of your training data, obviously your model has become more complex, right? The coefficients and your model is complex. So it is nothing but, in a way, memorizing the training data. It's like lookup table. It is like mug up of an answer for a question that some of us might have used this technique during our childhood. We mug up the questions, 10, 20, 30, 100, or 3, 4 in each chapter, and 5 chapters for that exam. And if the same question with same phrasing comes in, and we are ready to give the answer because we know each word. But if the question is twisted, that's where the brakes start falling in our mind, right? It's the same model, same case, same analogy for overfitted model as well, right? Because it is not understanding the pattern beyond the training. So it memorizes. It's also called a lookup. It's essentially maintaining a joint probability table or joint response table. What was the input? What is the output? Solution is, if you regularize and you cross-validate, you simplify the model and increase the training data. So one way to look at it, get all the data that's possible, which is impossible. But if you get all the data that's possible to predict and train it, then it's like, okay, if this is the input, this is the output. So lookup table, but it is impossible. I mean, it's not called prediction, right? It's called like our 1 to 100 tables, right? The tables that we used to say 2 times 5 is 10, 2 times 6 is 12, etc. That's not possible. Then it's not prediction. This is not intelligence, right? And this is not learning, right? It's mugging up. There's a huge difference between learning and mug up, right? And on the converse, or rather conversely, underfitting. So let's decompose these two syllables here, under or 2 words, under and fitting. So something is fitted less than needed. So here, there are 2 terms in our Telugu language, which originate from Sanskrit: Ativrishti and Anavrishti. So overfitting is Ativrishti, underfitting is Anavrishti, lack of it, right? And so the model is too simple to capture the underlying patterns, which means it's a sparse training data, lack of data. And the model is trained, it's simple, and its coefficients are trained with very minimal data. So while it did not carry the noise, but it also did not carry a lot of the patterns, unabridged, lack of resources, or lack of, usually it's called in the context of rain, right? Lack of rain or lack of pattern here. So what are the characteristics of this? Low accuracy, obviously, because your model is not capturing the inputs. And then it is not accurate, rather it is low accurate because it is not capturing the relationships or the latent patterns of the data by means of the mathematical models. And of course, it's too simple. So of course, we need some more complex model in terms of building the model, training the model with more data, and potentially more features. Complexity usually is a combination of more features and more data, and usually it is more features, right? And of course, not having any bias or lesser bias. You can compensate by having a higher bias at the underfitting, but it is not recommended. So regularization essentially brings in or addresses the underfitting, overfitting part particularly, right? So it essentially generalizes the model, right? Reduces the noise levels. How does it do? It adds some sort of penalty to the loss function. This is how the Python libraries implement when you call just the regularization function, right? So by adding the penalty, the model has been forced to essentially, the loss function is inhibiting the model from finding the patterns that are over assigned or large values than its importance or than its contribution to the pattern, right? So this will result in small decrease in the training accuracy rather than a bigger decrease, which is what we saw, 60% versus 68% accuracy, 8% improvement because of the regularization. But it is improving the generalizability for unforeseen data. It is improving the generalizability of the model for the unforeseen data. And there are various techniques of regularizations, L1 regularization, L2 elastic. I'm not going to go into it, but these are just key terms for you to go dig deep in and understand and how they are related, how they achieve this, what's the mathematics behind it, etc. Right? We looked at SMART, we looked at regularization and feature scaling, feature scaling, standardizing it. So what is standardization? Essentially, centralizing the data and bringing the variance to 1, right? It brings all the features into the realm, the data realm of related nearby realm rather than huge gap, right? It helps in having the model during the training converge faster. So that means your training time would be shorter relatively than not having a standardized training data. Stable prediction. So hyperparameter tuning, we'll also address this. So we'll have to tune certain parameters manually, not automatically. The coefficients, weights are tuned and found automatically using training, using the techniques, mathematical models, optimization, finding the loss, blah, 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 objective function, etc., right? Whereas the hyperparameters are chosen by you based on various experiences, right? Some of these are the regularization related, and what type of solver or what type of model. Essentially, solver is nothing but your optimization technique. There are multiple optimization techniques. We talked about it, right? One is the least squares, and there are other ways of optimization techniques, right? Convex optimization techniques. These are all advanced topics of how models are built, or optimization models are built, which are used by the machine learning models, right? So essentially here in our project, we use a inbuilt parameter set called grid search parameter set for C, which is related to regularization. Other one is the V, which is your solver, right? So there are two parameters that we use here to choose to set. We'll look at that code. One is the C is the inverse of the regularization strength, which is nothing but C value is inverse of the regularization strength. This value, C value, indicates a stronger regularization, because we want a strong the data to be model to be regularized, model to reduce the noise and carry the generalized patterns of the data when the value is around point, obviously less than 1, right? It will help prevent the overfitting. We addressed that, right? And it'll penalize the larger coefficient values, which are your weights. Larger the value, yeah, it's not 1. It can be any two-digit integer value or decimal value. The larger the C value, the regulation effect is reduced to be more flexible, the model to be more flexible and fit the data. Solver is, there are two solvers. One is, there is a ridge regression, and then there is a saga. So we are using saga, I think, linear and then saga. These are again various optimization techniques I'm not going to go into, but I want you guys to dig deep in. That's the way for you to build more knowledge and being more or bringing more expertise about these machine learning models, the building blocks, right? The feature importance is to see which one is contributing more, and this is straightforward, right? We've also seen in the logistic regression. Let's go back to the code. So here we have around 10 minutes. We have, yeah, so here we've used the smooth. We are setting the random state to 42 so that the training samples are there consistent and they are predictable. Every time we run, we use the same samples, or we get the same prediction accuracy. Then we are fitting we're training it, and then we are splitting for the training and splitting the input and the response for the training here. Then we are standardizing the data. Okay. And we've standardized based on the smooth. And we see here, here this part has already done balancing the output class by synthetically creating the rows and adding to the training data. Again, this is all automatically done by the open libraries that we've used. Right? And then, of course, the grid series search, parameter grid. See the regularization, inverse of the regularization strength, C, and then the solver among these two. We are saying use one of these two. Right? And then we are fitting the data and essentially building the model. Right? And we build. And then it's asking, essentially, pick the best one among the two solvers, whichever has the better accuracy. And that's what it's doing here. And then we are building, we are getting the accuracy levels for the train validation, which is 20% of 3 lakhs change. And then we are plotting the confusion matrix here. And also the prediction slash classification report, the F1 score and those 4 or 5 parameters we look at it. And we're plotting the receiver operating characteristic curve, ROC curve. Of course, we're adding watermarks, etc. And precision recall curve, 2-dimensional, and the feature importance here, we're plotting feature importance. And then we are what the project has asked. So it has given a separate test set. So predict for those that test set, only the ID and then the response. And then create a CSV file out of it. Right? So no values missing. No values missing. And these are the obviously the grid search CV, the parameter grid. Accuracy using the SMOT is 68% because data is highly biased towards 0th class, not interested. It's obvious, right? So classification report, precision is this much. So precision for identifying the no's are not interested is higher than precision for identifying the interested or yes, right? So recall specificity. And then the F1 score, which is the ratio, this is higher, but this is lower. And of course, support is in terms of what is the support value, the number of values that have zeros for this prediction, 66,000 change. Whereas here, it has only 9,500 change, right? We saw that. Some of which here, some of which we have predicted as false. We call it, we predicted this as 1, whereas supposed to be 1. So it's a false natives, right? Out of 7,009, 9,500 support, around 1,000 change were predicted as false natives, right? So accuracy, 68% change. Don't worry about this. These are a little advanced, and I'm just ignore it, right? So ROC curve. So obviously we want the curve to be with area 1, where somewhere here, 1 for false positive rate. False positive should be 0. So essentially somewhere here, false positive should be 0. True positive should be high, 1 here, this part. Precision recall. So we want here, this has to be, recall should be 1, precision should be 1, somewhere here we want in this curve. And this is the feature importance. Obviously, previously insured, we know, I mean, this is no brainer, right? If somebody has a vehicle insurance earlier, he would like to insure from ICICI Lombard as well. So that's no brainer. So some of these are straightforward as well, but mathematics will help us establish to take out that, the human variations, which are non-data based, right? It's all perceived without any data, whereas the models are opposite of perceived. They are deterministic based on the data, right? But sometimes, data not necessarily be true. That gets into beyond physics or metaphysics, right? So let's not go there. So that's about it. So one point that I'd like you guys to take home as a exercise is, I have not coded a model without using SMOT and without using a simple model without choosing any solver or regression strength. So one point that I'd like you guys to try out back as a homework is, build a simple model without any of this, any of SMOT, any of balancing the imbalance, and see what is the accuracy. Is this 68? Would that be 68? Or was it more than 68 accuracy, this value that I have highlighted, or will it be less than this? Right? Any guess, if you build such a simple model without SMOT, its accuracy would be more than 68 or less than 68? Any guess?
Sir, less than 68.
Right. Well, the common sense says that it should be less than 68. So I'd like one of you or all of you to try out a simple model and tell me what is the accuracy, validation accuracy with simple model, right? All right, that is what I wanted to cover. We have 4 more minutes. Any questions? Any questions, comments, queries, guys? How is the semester going on so far? Good? All right. So you guys seem to be little, not really forthcoming in having open chat, right? Nonetheless, if there are any questions, I'll wait for another few seconds to address if there are any questions, and if none, we can wrap up. Would you like to add anything, Professor Suresh, if you're there? All right. So, any questions, guys? Going last. If no questions, we'll wrap up the session. So try to complete the assignment. And what's the next week's topic? Anybody remembers? No one remembers. I think it's SVM, not the Cine Hall, but support vector machines. What are support vector machines? It's a little advanced model, little complex model, little involved model in terms of the concepts and mathematics as well. So I'll try to address as simplistically as possible, taking the mathematics out of it as much as possible, but only the necessary mathematics. And probably we'll try to choose a project that we have done in the past, one of these two, if we can use. If not, I'll try to pick something that I have done with IIT Kanpur as part of my master's. Right. All right, guys, if there are no questions, and I hope you have picked up something from today's session, complete the project implementation and submit it by, when is the last date to submit the project? This project, guys?
Thursday, sir. Thursday.
Okay. Did all of you submit the linear regression and PCA? Obviously no, but please try to submit. Doesn't matter even if the time is, I think I've extended the submission date, but if you have completed after the submission date and it is not allowing you to submit, please write to me through email. I think you have my email from the GPREC. I think it's Venkat something. Venkat. What was that email? Do you guys have my GPREC email address? Yeah, this is the one. Write back to me here. I will open up the submission. Okay, guys? Thank you very much. But please do not forget to complete the project, because out of 6 or 8 models, we would consider at least more than 50% for conferring the certificate to you guys on the closure of this program, which would be probably 1st or 2nd week of November, where I would be personally handing over. We would be personally handing over these certificates. I think probably your principal or somebody would invite a chief guest. Okay, guys. Thank you very much and have a good weekend and all the very best. Bye-bye, guys.
Thank you, sir.
Stopping the recording.